In the case of eccentric loading, we'll discuss the two cases. In the first case, we have two plates which are to be welded and a point force is applied. So this force F is in the same plane in which we have done the welding. Suppose we do the welding here on the top. So the plane of welding and the plane of the force is in the same. Suppose we want to do the welding here also. In that case also, we have the force in the same plane. Even you can do the welding from bottom side also. So any of these cases we have to consider. Either we can have a top weld or we can have the vertical edge on this side as well as on back side, or we have full U type of welding. But this time the force F and the plane of weld is in the same plane. As you apply the force here, this plate will going to turn in a clockwise direction. As the plane will rotate over the another plate, so there is a chance of shear is developed and we have the torque is developed. This torque is same as the force F multiplied by the eccentric distance E. Eccentricity you have to measure from the CG of the weld group. So here distance E represents here the distance between the CG of the weld group and the line of action of the force. Since the second plate on which the force is acting will going to turn in the clockwise direction above the gusset plate, so there is a torsion will develop. We can show the torsion in the same plane. Let's consider we have a weld on the top, that is this one is representing the weld on top and this one is representing the weld at bottom. Now these two weld lengths are almost symmetrical in length, so we can locate here the centroid. Now because of symmetry, the centroid will be at this point, that equal to C, and you have to measure the distance between the line of action and the given centroid. So the distance between the center of gravity and the line of action of a force is called as eccentricity. So this one is the case representing the shear in a weld when the plane of torsion is in the same plane, that of weld. The second case is slightly different as compared to the first case. So this one is a gusset plate and again one plate we have welded here. So we have done the welding on the top side here. So welding is done on the top side. So this plane and the welding plane is one and same plane. And the welding is done on the bottom side also over this length. But the plane of the force F and the plane of weld are different this time. So clearly observed here is that the given torsion it will develop. Basically not a torsion here, it's a basically bending moment will develop in the second case because this plate will going to bend. So that bending will occur in this plane. So we have to show the bending here, that equal to M. Now this time the force is acting in this plane and the weld is acting at the gusset plate. So these two planes are different planes, so that is our case number 2. And in the case number 1, we have plane of welding and the plane of force is same. So here we have the torque is developed in this plane. See, the weld and the force are in the same plane, then the weld is subjected to one vertical force F and one torsion, that is F into E. In this case, when the weld and the force plane are different, then the weld is subjected to one force F and one is due to bending moment. Again this time the eccentricity will be same here. This one is our centroid and this perpendicular distance which is measured along this horizontal plate will be equal to E, and we have bending moment M will be equal to F multiplied by E. So this one is subjected to bending moment and this one is subjected to torsion. Now how to solve this problem? First you have to get the concept of eccentricity. For eccentricity we must know how to find out the value of center of gravity of the weld group. Once you locate the center of gravity, that is the centroid of the weld group, then you can measure the distance between the centroid and the line of action of force and you can find out eccentricity. Two type of stresses will occur here. One is due to the force F, that we equal to tau. Let's say tau prime will be equal to force F divided by the weld area equal to A, and the second shear stress is developed, that equal to tau double prime will be due to torsion. Torsion stress is given as T divided by R divided by J, where J is the polar moment of inertia. In this case, again, two stresses is developed. One is a primary shear equal to tau prime is equal to force upon area, and one bending stress is developed that will be equal to m into y divided by the moment of inertia I. So you have to find out here the moment of inertia of the weld group. Here we have to find out the polar moment of inertia. So lot of basic thing we have to discuss first, how to calculate the center of gravity of the weld group, that is first part. Then second part is to find out the value of eccentricity. Next part is to calculate the polar moment of inertia or moment of inertia. Now consider the first case here. We have done the welding on one side only, that is the line welding of length equal to d, and we have throat thickness equal to t. Throat thickness is very less as compared to d. This one is the centroid of the weld groove system. Let's say this axis is x, which one is the centroidal axis. This axis is y, which is again a centroidal axis. Moment of inertia about the centroidal axis in a standard form is given as b into d cube divided by 12. This time the b is same as equal to t and the d value is equal to d. So we have ix is equal to t multiplied by d cube divided by 12. Similarly, the moment of inertia about the centroidal axis y is represented as iy is given as exactly opposite, that is db cube by 12. db cube divided by 12. This time the d will be as it is, b is replaced as t, so this value is equal to d multiplied by t cube divided by 12. As far as the t is very less than t, so we can claim here that the t cube quantity is very less as compared to d cube, so the contribution of this quantity is small. So we can approximate it here. Iy is approximately equal to 0. And we have value of ix is equal to t multiplied by d cube divided by 12. The polar moment of inertia J will be same as equal to ix plus iy. But the contribution is iy is 0, so polar moment of inertia is same as ix. So we have this time the J will be equal to t multiplied by d cube divided by 12. So here the cube of the weld thickness is very small and hence can be neglected in the contribution of iy. Only the ix value you have to consider, and the polar moment of inertia is J, which is ix plus iy, is given as t into d cube by 12. So this value of t will appear continuously. Suppose we prefer to do the welding only on the top side, that is this side. So welding is done up to length equal to d. So this welding will be shown here. So this distance will be same as equal to d and t is the thickness. Again we want to calculate ix and iy, that is the moment of inertia with the centroidal axis. So ix will be same as breadth multiplied by depth cube divided by 12. We have breadth is equal to d, height is equal to t cube divided by 12, and we have iy is equal to depth multiplied by breadth cube. So we have depth is t and the breadth which is equal to d. So we have t d cube divided by 12. Since we know here the value of t is very less as compared to the length of weld, that is the throat thickness is very small as compared to the length of weld, so the contribution of ix will be equal to 0 and the contribution of iy will be equal to t into d cube divided by 12. So almost same answer we'll get in as the previous case. Only previously ix is introduced and now iy is introduced. As far as the polar moment of inertia is considered, J is equal to ix plus iy. Here ix value will be equal to 0, but the iy value exists, that equal to t into d cube divided by 12. So this value is same as equal to t into d cube divided by 12, which is same as the previous value when the welding is done vertically is t into d cube by 12. So in this fashion we have the welding is done on one line. Now consider here we have done the welding on this edge as well as on the back edge. So we can show the welding here. So this one is the welding is done and one welding is done on the back side. So this weld and other side weld you can visualize here now. This one is the same as our force. This one is our weld group. Here D represents the length of the weld and B is the distance between the two welds. Now these two are the symmetrical welding. So this position represent here the centroid C or G, and from this point to the line of action of force we have to measure the distance that will be called as eccentricity. So from centroid C, if you measure the perpendicular distance between the line of action of force is called as eccentricity E, and this one is representing the throat thickness equal to T. Let's consider we have two parallel welds which are vertical. Let's say here this vertical distance is equal to D and the horizontal distance equal to B. Due to symmetry we can locate the centroid here. The coordinate of centroid will be x bar and y bar is same as equal to C B by 2 and D by 2, B by 2 and D by 2. This one is a centroid. So in this case we have area of the one weld will be equal to 0.707 multiplied by H, that is a leg size, multiplied by D. Since we have two weld here, so you have to multiply by 2. So we'll get this answer close to 1.414 multiplied by H multiplied by D. So this one is the resultant CG through which we are interested to know what is the moment of inertia about the x-axis and y-axis. To explain this I have just increased the thickness of the weld, but actually it's a very thin weld. For the left hand side we have x1 and y1 are the centroidal axis. This one is x2 and y2 is the centroidal axis. This one is same as our throat thickness equal to T, which will assume to be equal to very small as compared to the length of weld. So value of T is very less as compared to D. The moment of inertia about the centroidal axis Ix is given as B into h cube, that is the breadth multiplied by height cube divided by 12, and moment of inertia of a rectangle about y-axis is given as h into b cube divided by 12. So we have Ix1 and Ix2 is identical value. So we have Ix1 is same as equal to Ix2 is equal to B. B is the breadth, breadth is T, into height, height is D, that is BD cube divided by 12. And we have Iy1 equal to Iy2 is height into breadth cube divided by 12. This time we have height is same as equal to D and the width is equal to T, that is the breadth is equal to T. So we have T cube divided by 12. T cube is very small quantity, so approximately this value we can neglect and we'll make it equal to 0. So we can transfer the moment of inertia Ix1, Ix2 on x-axis. For that one we'll use the parallel axis. The distance between x and x1 is equal to 0. The perpendicular distance between x and x2 is equal to 0. So by parallel axis theorem we have the moment of inertia about the x-axis is equal to Ix1 plus we have area A1 multiplied by perpendicular distance square plus we have Ix2 plus we have area A2 multiplied by perpendicular distance square. Ix1 is same as Ix2, so we have 2 times of Ix1 and perpendicular distance is 0, so second quantity will be equal to 0. So moment of inertia this time will be equal to Ix1 plus Ix2, that is 2 times. So we have 2 times of T into D cube divided by 12. So this value of Ix is equal to T into D cube divided by 6. So remember this formula when we have the weld are vertical. For two vertical weld, we'll calculate here the polar moment of inertia. As per the definition of polar moment of inertia is given as J, which is equal to Ix plus Iy. This polar moment of inertia is nothing but Iz, that is the moment of inertia about the Z axis. So you have to draw here perpendicular to X and Y that represent the Z axis. So about this axis we want to calculate the polar moment of inertia for two vertical weld. Ix1 is and Ix2 is equal to Td cube by 12 and Iy1 and Iy2 is equal to d into T cube by 12, which is approximate equal to 0. Let's say this axis is equal to Z2 axis and this axis is equal to Z1 axis. So we have polar moment of inertia for the right hand side weld is equal to J1 and we have J1 equal to Ix1 plus Iy1. Out of that we have Ix1 is equal to T into D cube by 12, T into D cube by 12 and Iy1 is equal to 0. It means that we have J1 is same as equal to T into D cube divided by 12. Similarly, we can calculate the polar moment of inertia about the Z2 axis, that is J2. So we have J2 is equal to Iz2. Iz2 is same as equal to Ix2 plus Iy2. Again we have Ix2 is equal to Td cube by 12 and the second value is equal to 0. So there is no meaning of Iy2 because that value is equal to 0. J2 is the polar moment of inertia of the left hand side weld is equal to T into D cube divided by 12. But we are interested to know the polar moment of inertia about the Z axis, and for this one we require a perpendicular distance between Z and Z1. The perpendicular distance between Z and Z2 axis is same as equal to the distance between C and C2 is equal to this distance, and this distance is same as equal to B by 2. Whereas the distance between the centroid C1, that is Z1 and Z, will be equal to distance between C and C1 is equal to again B by 2. So we have perpendicular distance between Z and Z1, Z and Z1 is same as equal to the distance between C and C1 is equal to B by 2. So that we called as R1 is equal to B by 2. Similarly, the perpendicular distance between Z and Z2, that is between C and C2 is equal to B by 2, that we called as R2 is again B by 2. So if I apply the parallel axis theorem, then we can calculate the total polar moment of inertia will be J1 plus area A1. So we have area A1 is equal to the length of weld equal to D multiplied by thickness equal to T. Similarly, we have A2 is also equal to D multiplied by T. So we have A1 multiplied by R1 square plus we have J2 plus we have A2 into R2 square. Now J1 and J2 is same here. So we have J1 is same as equal to J2, R1 is same as equal to R2, A1 is same as equal to A2. So this quantity is simply 2 times of J1 plus A1 into R1 square. That is, we have 2 times of J1. We have J1 is equal to Td cube by 12, T into D cube by 12 plus we have A1 is equal to D into T, dt. R1 is equal to B by 2, that is B square divided by 4. So we get 2 and 12 is 6. So we have Td cube divided by 6 plus D T B square divided by 2 and 4. So that equal to 2. Here we can take out T and D common. So we have taken out T and D common. What is left is D square divided by 6 plus we have D and T taken common. So we have B square divided by 2. So we have T into D. This time LCM will be equal to 6. We have D square plus 3 times of b square. So this one is the polar moment of inertia if the welds are vertical. Same value we will get in the table also. Only table they will give you Ju, that is d into d square plus 3 times of b square by 6. So d represent here the vertical distance and b represent here the horizontal distance. In the data table you will find the value of unit second moment of area, that is represented by Iu, and the unit polar moment of inertia, that is represented by Ju. In this case the thickness T was taken equal to 1, and therefore they will call it as the unit second moment of area and the unit polar moment of area. And to calculate the second moment of area I is equal to T multiplied by Iu. So total moment of inertia is nothing but the throat thickness multiplied by unit second moment of area. Similarly, the J is given as throat thickness multiplied by Ju, that is the unit polar moment of area. Your result is remain same. Only for simplicity, they have taken the value of thickness equal to 1. Suppose we have done the line weld and we have D is the length of weld. This time the thickness was taken equal to 1, that is they are called as the unit second moment of area. This one is position of G. In the table you will get this value of Iu is equal to dq divided by 12. Therefore the value of I will be equal to T multiplied by Iu. So we have get the value of I is equal to T into dq divided by 12. So when we have considered the weld and we have derived it by first principle, we also get the value of moment of inertia equal to T into d cube by 12. So our results will match here. Similarly, we have Ju is given as d cube divided by 12. So we have total polar moment of area is just obtained by multiplying T with the unit polar moment of area. That is, we have T into d cube divided by 12. Then we have considered two parallel weld having the length of weld equal to d and the throat thickness equal to t. In the table you will get this value T is equal to 1 and b is the distance. So by symmetry you can locate the centroid somewhere here, that equal to C is b by 2 and d by 2, that you know. In the table you will get this value as Iu is equal to d cube divided by 6. So we have total moment of inertia is obtained by multiplying T with unit second moment of area, that is T into d cube divided by 6. So by deriving the first principle, we also got the same result. The moment of inertia above the centroid is T d cube by 6, that is the second moment of area. Unit polar moment of area Ju is given as d multiplied by 3b square plus d square and is divided by 6. In that case we have total polar moment of area J is obtained just by multiplying T, that is T into d into 3b square plus d square divided by 6. And for other L type of welding is done, then data is available in the data book. Even for U shape data is available, and we have the two parallel vertical and two parallel horizontal. In that case we have value of Ju is a straightforward value, therefore I am giving you this value is equal to b plus d whole cube divided by 6. And we have Iu value, that is we have unit second moment of area Iu is given as d square by 6 into 3 times of b plus d. Actually it's a time consuming process, otherwise we can derive all these equations. Simple two equations we have derived. So whenever you have to solve the problem, you can take the table help and use the value of unit second moment of area multiplied by T to find out total moment of area. Then you can use the unit polar moment of area, that is the value of Ju multiplied by T to obtain the value of total polar moment of area. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.